Hello everyone, my name is Robin and I'm excited to be here today to talk about a critical technology in modern aviation, sensor data fusion in avionics. So we'll be exploring how the technology enhances safety, accuracy and the growing autonomy of aircraft. Over the next couple of minutes, we'll dive deep into what sensor fusion is, how it works and where it is headed. Now let's begin by understanding what we mean when we talk about sensor data fusion and why it is so essential in the aviation world. So, in simply put, sensor data fusion is the process of combining data from multiple sensors to produce more accurate, complete, and dependable information that could be obtained from any single sensor alone. Think of it like human perception. We use our eyes, ears, and sense of balance together to understand our surroundings. An aircraft does the same, but with a suite of high tech sensors. The importance of this in modern avionics cannot be overstated. It is the backbone of everything from basic navigation to advanced autonomous flight. The key objectives for today are to understand the what and why of sensor fusion, explore the different methods used, and look at real world examples and applications and also the future trends. Now that we have a general understanding of sensor fusion, let's take a closer look at the various sensors that make this possible in modern aircraft. So the modern aircraft are packed with a variety of sensors. Let's quickly go over the main players, starting off with the radar, which stands for radio detection and ranging. Now, radar is crucial for detecting objects like other aircraft or weather systems. Let's watch an animation to break it down. So, as the animation suggests, there's a device called as magnetron, which generates high-powered radio waves. Now, these waves are focused into a beam and are transmitted by the antenna. Traveling at the speed of light, these waves hit an object, like another aeroplane, and bounce off. A portion of those reflected waves travel back and are captured by the same antenna. A computer then analyzes the return signal based on the time it took for the wave to travel out and back. It calculates the range to the object. The direction the antenna was pointing gives us the object's bearing, and this is how radar sees the world, providing critical information for collision avoidance and weather detection. Next is the Global Navigation Satellite System, or the GNSS, which is the backbone of modern flight navigation. To understand how it all comes together, from the satellites in space to the integrity checks inside the cockpit, let's have a small animation. As the animation illustrates, modern aircraft uses satellite navigation for more direct routing using waypoints, which saves significant time and fuel compared to older ground-based navigation aids. The system known as GNSS is actually a combination of two key parts: the familiar GPS and crucial augmentation systems. While we often just say GPS, GNSS include multiple global satellite constellations like Russia's GLONASS and Europe's Galileo, making it truly robust international system. To compute a position, the aircraft receiver needs signals from at least 4 satellites. As you can see, 3 are used to calculate its 3D position, that is, latitude, longitude, and altitude. The fourth satellite provides an extremely precise time signal from its onboard atomic clock, which is crucial for an accurate fix. But for aviation, just getting a position isn't enough. We need to guarantee its accuracy, integrity, and availability. This is where augmentation systems come in. One onboard method is receiver autonomous integrity monitoring. The receiver uses an extra fifth satellite to cross-check the others. If it detects a faulty signal, it performs fault detection and exclusion to ignore the bad data. And in a perfect example of sensor fusion, aircraft autonomous integrity monitoring compares the GNS position with another onboard sensor, like the inertial navigation system, to ensure the two independent sources agree. Now, these onboard checks are what make satellite navigation safe and trustworthy for every flight. We also have infrared sensors that detect heat signatures and are especially useful in military or search and rescue operations. And finally, we have LiDAR. It's similar in principle to radar, but uses laser light to extremely high resolution mapping. As we can see, a LiDAR system fires out pulses of laser light. These light pulses bounce off objects like the ground, buildings, or other obstacles, and the reflected light returns to the sensor. The system measures the precise time it takes for each pulse to return. Since we know the speed of light, this time of flight measurements give us an exact distance to the object that the light pulse hit. By sending out millions of these pulses per second, The LiDAR unit creates a dense, three-dimensional point cloud of its surroundings. Now, this provides a highly detailed and accurate 3D map of the environment, which is invaluable for tasks like terrain mapping, obstacle avoidance during landing, and autonomous navigation. Now, clearly, each sensor brings unique strengths, but they also have certain limitations. Now, we'll examine how they are compared, and why we need fusion in the first place. Crucially, no single sensor is perfect. Their individual strengths and weaknesses are the very reason we need fusion. Let's start with radar. Its greatest strength is its excellent long-range capability, but it can struggle in cluttered environments. GNS, like GPS, is incredibly accurate for positioning, but its signal is weak and can be disruptive. For aviation, its raw signal isn't enough. Its integrity must be guaranteed. The IMU is fantastic because it requires no external signals. However, it's prone to small errors that accumulate over time, an issue known as drift. Then, the infrared sensors are passive and stealthy, but their performance can be degraded by external factors such as cloud, fog, or rain. To overcome these shortcomings and capitalize on the strength of each sensor, we use different levels of fusions. Let's explore how that works. Sensor fusion isn't a one-size-fits-all process. It can happen at different levels. At the lowest level, we have data level fusion, where raw data from similar sensors is directly combined. This is computationally intensive but can provide the most detailed result. Next, we have feature level fusion. Here, we first extract specific features like the size, speed, or shape of an object from each sensor data, and then we fuse these features. And finally, there's decision level fusion, where each sensor system makes its own preliminary conclusion. For example, I think there is an obstacle. The fusion system that combines these individual decisions to make a final, more reliable judgment. But fusion doesn't just vary in depth, it also varies in structure, and we'll have a look at how fusion systems are architected. How we organize the flow of data leads to different fusion architectures. In a centralized architecture, all raw sensor data is sent to a single, powerful processor for fusion. This is optimal, but it creates a single point of failure. In a distributed system, each sensor processes its own data locally and then shares its results with other sensors. This is more resilient. And lastly, a hierarchical architecture is a hybrid approach offering a balance between the centralized and distributed models. Now, the choice of architecture purely depends on the specific application, balancing performance, redundancy, and cost. Regardless of the architecture, the core of fusion always lies in the algorithms. Let's now explore the most fundamental one, that is the Kalman filter. Kalman filter is an incredibly powerful and mathematical optimal tool for estimating the state of a system, like an aircraft's exact position and velocity, even when the sensor measurements are noisy and imperfect. The core idea is a continuous two-step cycle of predicting and then correcting. The filter operates in the elegant predict-update cycle. First, it predicts the system's next state based on its internal model. Then it updates that prediction using the actual sensor measurement, intelligently weighing the new information with a factor called the Kalman gain. This continuous predict and correct process is what allows us to fuse a model's prediction with noisy sensor data to get a single, highly accurate and reliable estimate of the aircraft's true state. But not all systems are linear, and that's where more advanced variants of the Kalman filter come into play. The standard Kalman filter is great, but as mentioned above, many real-world systems aren't perfectly linear. That's where its variants come in. The extended Kalman filter linearizes the system around the current state estimate. The unscented Kalman filter offers a better approach for highly nonlinear systems. And lastly, the ensemble Kalman filter is used for extremely complex systems like weather modeling. In avionics, the EKF and the UKF are commonly used for integrating GPS and IOM data, providing a smooth and accurate navigation solution even if the GPS is temporarily lost. Beyond Kalman filters, there are other probabilistic methods that offer even more flexibility, especially for complex environment. A prominent example is the particle filter. Unlike Kalman filters, which assume a simple Gaussian distribution, particle filters can represent any arbitrary probability distribution. They do this by using thousands of particles to present different possible states. Each particle represents a guess, and as the new data comes in, these guesses are re-evaluated, with the most likely ones retained and refined. This makes particle filters excellent for highly non-linear, non-Gaussian problems such as tracking a maneuvering target through complex terrain. Now that we have seen how fusion algorithms work in theory, let's move to the cockpit and explore how they are applied in the real world commercial aviation. So modern commercial aircraft like the Airbus A350 and the Boeing 787 are the flying examples of advanced sensor fusions. Their air data inertial reference units, also called as the ADIRU, are a prime example. These units fuse data from air data modules, accelerometers, and gyroscopes to provide precise altitude, airspeed, and attitude. This fused data feeds directly into the autopilot and is critical for terrain and weather avoidance systems, providing pilots with a clear synthetic view of the outside world even in zero visibility conditions. Commercial aircraft rely on sensor fusion for safe and efficient travel, but in the domain of military, the stakes and capabilities are on a whole different level. Let's see how fusion powers the F-35 fighter jet. The F-35 is essentially a flying data fusion engine. It combines information from its own advanced radar, a 360-degree electro-optical distributed aperture system, also called as the DAS or DAS. It uses infrared sensors and electronic warfare systems. This DAS provides complete spherical IR coverage, detecting and tracking aircraft and missile launches from any direction. The data is then fused to create a single, unified tactical picture. To truly appreciate how this revolutionary technology works, words alone aren't enough. So let's take a look at a short video that explains or shows the distributed aperture system and pilot's helmet in action.
Pilots who fly the F-35 fighter jet wear a helmet that can see through the plane on all sides and is worth $400,000 US. Each helmet is fitted with noise-cancelling headphones, night vision, a forehead-mounted computer, and a TV screen-like projector that displays live video on its clear visor. But what really makes this helmet so special, when it's combined with the sensors and exterior cameras mounted to the F-35 fighter jet, it gives the pilot the equivalent of X-ray vision. So when the pilot looks down, they can see straight through their own body and the floor of the plane to the terrain below. The helmet also supplies such information as target identity and distance, and even advises which weapon to use. So when looking through the plane, if the pilot sees something that should be hit by a missile, or just wants to get a closer look, all he has to do is look at it to lock on, then flip a switch to zoom in or fire away. Because the helmet is custom made and costs $400,000 each, pilots don't get to use them during flight school and simulator training. It's not until they are assigned to an active duty F-35 squadron that they receive the most complex helmet ever made.
As we just saw, that fused data is projected directly onto the pilot's $400,000. Yes, you heard me right. The helmet cost a whopping $400,000. Now this gives the pilot what is effectively an X-ray vision, allowing them to look through the floor of the aircraft and see a fused sensor image of the ground below. This incredible level of situational awareness, where targets can be locked simply by looking at them, is a revolutionary leap in combat capability, and is all enabled by sensor fusion. As impressive as its capabilities are, building and maintaining such fusion systems comes with a host of technical challenges, and we'll explore a few of them. Despite the benefits, implementing sensor fusion, as mentioned, is not without its challenges. Real-time constraints are immense. Data must be processed in milliseconds, especially during critical phases of flight. Then there's the data association problem. If multiple objects are detected, how do you know which sensor measurements belong to which object? Redundancy and fault tolerance are also crucial. The system must be able to detect and reject faulty or compromised sensor data. And of course, there are cybersecurity threats. Sensor data must be protected from spoofing or manipulation, particularly in military and autonomous systems. To address some of these challenges and push fusion capabilities even further, AI and machine learning are now being incorporated into the fusion process. The future of sensor fusion is increasingly being driven by AI. Traditional filters rely on predefined mathematical models, but what if the solution or situation is too complex to model accurately? This is where neural networks come in. by feeding large data sets of sensor input and ground truth into a deep learning model. The system can learn complex relations on its own. This is particularly powerful for tasks like object recognition, where AI can fuse visual data from a camera, distance data from a LiDAR, and motion data from radar to classify and track objects more accurately than any one sensor could do on its own. And if AI is the near future, quantum technologies may well define the long term future of sensor fusion. Let's take a look at this exciting technology. Looking even further ahead, emergent technologies like quantum computing promise to transform avionics. Aerospace leaders like Airbus and Boeing are already investing heavily. Quantum computing can solve incredibly complex problems that are impossible for classical computers. This could lead to the design of new materials at the molecular level, creating lighter and stronger aircraft. Quantum inertial sensors may offer navigation thousands of times more stable than today's IMUs, especially drift-free and perfect for use when GPS is not available. And in the realm of cybersecurity, quantum-safe encryption will protect flight systems from future hacking threats. While still in development, these technologies offer a powerful glimpse into the future of ultra-precise, highly resilient avionics. With all this advancement, classic filters, AI-driven models, and quantum systems, it's clear that sensor fusion is the glue holding it all together. In conclusion, sensor fusion is the invisible engine driving modern aviation. It's what turns data into decisions, enhances safety, and makes the incredible capabilities of today's aircraft possible. As we move toward a more autonomous and data driven future, this technology will remain the cornerstone of how we fly smarter and safer. Thank you all for your attention.